Hi, Geometry Honors. We are starting now section 11.4, which is on surface area. And you've seen surface area before, but now we're going to be focusing on it within your geometry class. So what I decided to do is I took a box and I cut it up a little bit to help demonstrate what we're talking about with surface area. So you can see we have an ordinary box here. And basically, as we'll see in a moment in our notes, surface area basically is the sum of all the areas on all sides of the boxes, okay? So how can I see that better? Well, what I did is I cut this up so that basically you've got right here, we've got the top of the box. Right here, we've got the bottom of the box. We call those the bases, okay? Top and bottom, and they're, whoops, this is opening up a little bit on me already. Top and the bottom, and they're parallel to each other. So two sides that are parallel to each other, we can call the bases. And then we have around the sides of the box, and we'll see this in our notes in a little bit, we have the lateral faces. So if we take this all apart, we have, as you'll notice here, basically, I'll kind of step back a little bit so you can see all of it. We have a net, and you've probably seen this before, that basically you can take a solid and you can take it apart, and you can see that basically if we're trying to find the surface area of this solid, we can add up the areas. So we've got the top and we've got the bottom, right down here. What it's shaking right now is the bottom. And then we have the sides going across here. And if we add up each of these rectangles, the 6 rectangles that we see will give us the surface area of the entire box, okay? So I'm gonna pause a moment and then we'll start the regular part of the video. Okay, so in this section 11.4 on surface area, we're gonna be looking at surface area of prisms and cylinders, and also pyramids and cones. Now, the box that we just looked at that I had taken apart as a net is an example of a prism. And a prism is a solid that has 2 parallel bases. And they're named based on what the shape is on the base. So for example, here you can see in this particular diagram, and I know it's small, but you have this printed out as well. You can see that the top and the bottom, these 2 pentagons that are parallel to each other are the bases, and then the sides we call the lateral faces. So it's kind of like what we just saw in the cardboard box. The top and the bottom of the cardboard box were the bases, and then the sides were the lateral faces, okay? And so we call, for example, a box a rectangular prism because the top and the bottom are rectangles. We call this a pentagonal prism because the bases, the top and the bottom, are pentagons. And when I say the top and the bottom, obviously I could rotate this side to side and we can have those, what was the top and the bottom, the left side and the right side. Basically, the pair of sides that are opposite one another and parallel are going to be the bases, okay? So lateral and surface areas are what we're going to be looking at. In a solid figure, we just said faces that are not bases are lateral faces, and the lateral area is the sum of the areas of the lateral faces, okay? So if I want the total surface area, I'm going to take the sum of the areas of the lateral faces and the areas of the faces that are bases. Okay, and so we have steps that we can use to help you to follow to find the surface area. Okay, first step, so you make sure you don't leave any sides out, is count the faces. Remember we counted on the box that there were 6 sides to the box, 6 faces, when we could see that by looking at the net. including, when we count the faces, we're including the bases and the lateral faces. Okay? We find the area of each face. Okay? And then add the area of the faces to find the total surface area. Okay? So we're going to start here by looking at prisms and cylinders, and the second part of this lesson we will look at pyramids and cones. Okay? So as we said, a prism has two parallel, congruent sides that are bases, and the bases are connected by the lateral faces. Okay, and the lateral faces are parallelograms. And of course, we know, like if we look, for example, at this diagram here, you can see that in several situations here, those lateral faces are not just parallelograms, they're also rectangles, okay? So let's look closely at the four diagrams we have down here and kind of see the differences, okay? So you'll notice here, in the cases here of the pentagonal prism here, and this one, this is the triangular prism, and notice I'm labeling these, this is pentagonal because the bases are pentagons. This is triangular prism because the bases are triangles. Here is a rectangular prism because the bases are rectangles. And if you want, you know, I can shade those in as well. So I could shade in, here's the base, and here's the base, right? And those bases are rectangles, and so that this is a rectangular prism. Okay, so let's look at this odd-looking solid down here, okay? Notice we call this an oblique triangular prism. So if you compare it, you know, you can see both of these with the blue bases and with the yellow bases here, both of these are triangular prisms. But in this triangular prism, the one triangle is directly on top of the other one. Whereas over here in this what we call oblique triangular prism, in any oblique prism or oblique solid, what happens is the bases are not directly on top of one another. They're still parallel and they're still congruent, but basically they're diagonal to one another. And so what you see is that the lateral side is a parallelogram. It's not a rectangle. Whereas in the cases of the rectangular prism here, pentagonal prism, this triangular prism, all of these are directly right on top, or, you know, side to side here, right? Right opposite one another, whereas here it's not. We call these right prisms, okay? So all of these are called right prisms because essentially you've got a right angle right here, okay? Whereas here, obviously, this is not a right angle. So if they're directly on top of one another, the prisms are called right prisms. If the bases are not directly on top of one another, they're oblique prisms. And I just want you to be familiar with that. We're actually not going to do any surface area calculations with oblique prisms, but you should be aware of what they are. Also, another thing that was interesting in this diagram that I pulled, and this is not just true of oblique prisms, but all of these prisms, that basically I can slice into that solid, and I have a slice that's a cross section, and that cross section, of course, is going to be congruent and parallel to the bases. So, I mean, I could do the same thing here with any one of these figures. I could create a cross section. For example, you know, right here, I could create a cross section. I could create another pentagon sliced right through there. That would be a cross section, okay? So the cross sections are not just for oblique prisms, it's just I happened to pull this diagram that showed the cross section, okay? So the lateral faces are parallelograms, and they are rectangles if it's a right prism, okay? So if it's a right prism, then you have rectangles on the lateral faces. Okay, so I'm just going to pause just for a moment, because before we actually discuss cylinders, what I want to do is just look at a can and show you what a cylinder is, you know, just by actually looking at the can. All right, so I'm going to pause for a moment so I can show you that can. Okay, so here we have a can, which of course is a cylinder in shape, okay? And of course we know that a cylinder has a top and a bottom. The top and the bottom are circles, okay? So if I were to calculate the surface area of a cylinder, I have two circles which are congruent and parallel that have the same area. So I can find this area of 1 and multiply it by 2 to get the area of the two circles together. But then think about what I have as well, all right? So what I want to show you here is I took the label of the can, it's still stuck on there, but you can see what I've got when you pull that off the can, we have a rectangle, okay? Now, we know that to calculate the area of a rectangle, we have a height. So that would be the shorter edge here, right? And that's the same as the height of the can. So where I'm touching right here, that's the height of the rectangle, and that's also the height of the can, okay? But think about what the base of the rectangle is, because the area of the rectangle is the base times the height, okay? Think about how I could calculate the base of this rectangle. In other words, the long side of the rectangle. So before I show you, I want you to think about it for a moment. So I'm going to wrap it around the can again. And think about the fact that if I wrap this label around the can, of course, ignoring the fact that there's a little bit of overlap here for a moment. So if we just cut off that little bit of overlap, think about what the length is or the bases of that rectangle. Okay, and if you think about it, hopefully you came up with the fact that it is that since we can wrap it around the can, the length or base of that rectangle is the same as the distance around the circle, which of course is the circumference of the circle. Okay, so in order to calculate surface area of a cylinder, we add in the two circles, plus we add in the area of that rectangle, and we'll see how to calculate that now. I'm just going to pause again to go back to looking at the paper. Okay, so as we just said, a cylinder is composed of two circles, the top and the bottom of the can, plus a rectangle, right? So basically the two circles are top and bottom, and the rectangle is the label of the can, right? So then if I want to calculate the surface area, which I'll just abbreviate SA, that's going to be the area of the bases, which are the circles, plus the lateral area. The lateral area is that outside of the can, the label, okay? So the lateral area is the rectangle that forms the label on the can. okay? So as far as a formula then, what we can say is the area of the bases, because you have two circles there, each circle has an area of pi r squared, but there are two of them, okay? So there are two circles, plus we have the area of the rectangle. But remember, the base of the rectangle is the circumference of the circle. So I can say that circumference of the circle is 2 pi r, or I could say pi d, depending on the situation, okay, times the height. So this is the circumference of the circle, which is also the base of the rectangle. And this is the height of the can, or the height of this, you could say the height of the cylinder, which you can also say is the height of the rectangle. Okay, and just remember here, you know, because we know circumference can also be written as pi d depending on the situation, we could also say or 2 pi r squared plus pi times the diameter times h, right? Because either way, whether we have radius or diameter, we're still going to get the same result, okay? So we're going to actually do some calculations here. One thing I will label here actually on this is just so we're clear, this is what we're talking about as the height of the can, right? And of course, this is the radius. And across the can, if I were given this whole distance across the can here, that would be the diameter, right? All right, so let's look at calculating the area of a rectangular solid. Like originally the the cardboard box that we were looking at when I had it taken apart as a net, okay? So we're going to be calculating the area of all the sides of this box all together, all right? So first of all, remember we want to count. We want to make sure we know how many pieces we need to have here, because if you don't consider all 6 sides, then you know you're not going to have the correct result, right? So we know that we have a top and a bottom, left and right, front and back, so that altogether gives us 6 sides. So make sure you recognize there are 6 sides. So make sure you consider all of those pieces when you're calculating the surface area. Okay? So let's look at the top and the bottom to start with. Let's start with the bases. Okay? One of the bases is 5 times 4, but there are 2 of them, right? Because if this length is 5, this length is 5. If this length is 4, then this length is 4. So we have 2 of those rectangles, and each one has an area of 5 times 4. Okay? So we might want to highlight it. Make sure we can find all those 6 sides. Here are 2 of the sides right there. Okay? Then let's look at this left and right. So let's mark this here. These are the bases, top and bottom. Okay? Then I've got the 2 sides, which are on the left and the right, 4 by 2, and then over here, 4 by 2. So 2 times 4 times 2. Okay? And this is going to be the left and right lateral sides. Okay? And so again, here now we've got 4 of the sides we've taken care of. Okay? And lastly, we've gotten top and bottom, left and right. Now we want front and back. Okay? So the front here, 5 by, realize if this is 2, then this is 2, right? And we can see the back, of course, is 5 times 2 as well. So we have 2 of those, 2 times 5 times 2. And again, I'm going to highlight, and then you've counted it up. We've got 2, 4, 6 sides we've accounted for. Okay? And this is going to be the front and the back. Okay? And so if we calculate all of that, this 2 times 5 times 4 is 40. 8 times 2 is 16. 10 times 2 is 20. Add that all up, and you'll get 76, and make sure you put the units, please. 76 centimeters squared would be the surface area. Okay, and if you want, you can either say area or SA if you want, just to remind you that you are calculating surface area here. Okay. All right, let's look at the right triangular prism. Okay, and let's count sides here. Altogether, we've got a base on the top and the bottom. That's 2 sides. We have a front, we have the back, and we have the right side. Okay, so altogether there, we have 5 sides. So make sure that you end up with 5 sides. Okay. So for the surface area here, and again, notice this is a triangular prism because your bases are triangles, right? Here's one base, and here's the other base, right? Just like over here, this was a rectangular prism because the top was a rectangle and the bottom was a rectangle, okay? All right, so what we can do now is we can, first of all, you can start with any ones you want, but I'm going to start with the bases here. Obviously, in this case here, I've got the base and the height of this triangle. You notice it's a right triangle, and therefore, to calculate its area, I just need to say 1/2 of the base times the height, okay? So I've got 2 of those though. So I'm going to say 2 of those, but then I'm going to say 1/2 of the base times the height. So the base times the height is 12 times 5. Okay, so 1/2 of base times height. And you might want to write that underneath, 1/2 of base times height, so you understand that we're talking about the areas of those triangles, right? So this is the triangular bases. Okay. Next, that took care of 2 out of the 5 sides. Okay. Now, unlike with the rectangular prism, these other 3 sides are not all going to be, none of them are going to be congruent to one another. So we have to consider each separately. So let's, for example, notice here the front. Okay, the front of this triangular prism is going to be, if we recognize here, we've got 12 times 10, right? Because if this side is 10, then this side is 10, right? So we're going to say that's a rectangle here, right? So because that's a rectangle, I'm just going to say there's just one of those, and I'm just going to add in 12 times 10. And that is going to be the front rectangle. Okay? Now let's go to the right side. Okay? So the right side we can see is a rectangle, 5 times 10. And then finally, we have the back here. Okay, now be careful with the back. The back you can see is 13 by 10. Okay, if you want, you could even label the bottom 13 here. You notice we have a Pythagorean triple here, 5, 12, 13, right? So we have 10 by 13 there, or 13 by 10. And that is going to be the back. Okay, so now watch, 2, 3, 4, 5, right? And so we've considered all 5 sides now, and we just need to do the multiplication and addition. Okay, so if you multiply this out, 60, half of 60 is 30, times 2 is going to be 60. 12 times 10 is 120. 5 times 10 is 50, and 13 times 10 is 130. Okay, if I add that all together, the surface area of the triangular prism is going to be 360 square centimeters. Okay? All right, so let's look at the right cylinder, and then we'll pause before we go on to pyramids and cones. Okay? So notice here what we're given for the right cylinder here. And again, this is called a right cylinder because the top and the bottom of the can, and I'll just kind of finish the edges right here. The top and the bottom are parallel and congruent to one another and directly on top of one another. Okay, so here are the bases. I'll highlight the bases for you. Okay. So the height of the can is 12 units. In this case, it doesn't say centimeters, inches, or whatever, so we'll just say 12 units. What's cut off on the bottom here, this distance is supposed to be 10. So we'll say that this is 10 units right here, so you can add that into your diagram. Now, that's the distance across the circle here, right? So understand the distance across the circle here is 10 units, which that means that that's the diameter. Okay? And of course, half of that is the radius. So if I consider from here to here, that's the radius, which is 5 units. Okay? Remember, to calculate the surface area, I just need to add in the areas of the two circles. And then I take the circumference, which is the length or the base of the rectangle, and multiply it by the height and add that in to get the area around the can, the lateral area, the label on the can. Okay, so remember how we get this. The surface area is going to be the two circles plus the lateral area. Okay, so in this case here, for the two circles, I will use the formula 2 pi r squared because pi r squared is the area of each circle. Now the lateral area, remember we're taking the base of the rectangle, which is the circumference of the can. So I can either say pi d or 2 pi r, it doesn't matter, because I have both the diameter and the radius here. But since I have the diameter, I'll just use the pi d times the height. Okay, so this is the circumference of the circle, which is also the base of the rectangle. And this is the height of the rectangle, which is also the height of the can. Okay, so I'll just fill in what I know. The radius is 5 units, so I'll square that. The diameter is 10 units. The height is 12 units. Okay, and we'll simplify this. So we'll have 2 times pi times 25 plus 10 times 12 is 120 times pi. Okay, so this is 50 pi plus 120 pi. All together, adding that together, since those are like terms because they both contain pi, I can say 170 pi and units squared. I can just leave it as units squared because I don't have any other specific units here, and I don't have to go any farther. I've got an exact value there, so there's no reason to round this. Okay, if they told me to round to a certain decimal place, I would do it, but otherwise, I'm just going to leave this as 170 pi units squared. Okay, so we'll pause for a moment before we go on to pyramids. And when I say, I'm pausing, I want you to pause and to review before you move on. Okay, so for pyramids and cones, we're going to find the surface area in the same manner that we had before. So this is what you took notes on before when we were doing the prisms and cylinders. We're going to first count the faces, including the bases and the lateral faces. We're going to find the area of each face and then add the areas of the faces to find the total area. Okay, so just to kind of give you a general idea here, what we have over here, we have 2 square pyramids. So these are both square pyramids. And of course, you know that these are cones. Okay, now a cone obviously is always going to have a circular base. Okay, and notice the difference here between a cone and a cylinder, of course, is that a cone has one base, whereas a cylinder has two bases. Same with pyramids versus prisms. A pyramid is named by its single base. So because the base here is a square, it's called a square pyramid. Okay, but as you'll see later on, we can have triangular pyramids. We have here, it's a little bit cut off, but we're going to fill in the rest of it. We can have an octagonal pyramid because the base is an octagon. So depending on what the base is, we're going to name that period based on that one base. Okay. What we're going to be noticing here also, and you can see it in this diagram very clearly, is that we have a height of a pyramid, and we also have a height of a cone, okay? And we'll call that height H, okay? But we also have a height of what we call a slant height, which is basically a height along the edge of the figure, okay, along the side of the figure. So there's a slant height here on this pyramid, and we also have a slant height here on this cone. Now the slant height we're going to call L, okay? And we also have in these other diagrams too, you can see we have the slant height here, we have a slant height here, and the interesting part also is to notice that even if we're not given the height within the figure, whether we draw that perpendicular distance inside the figure or outside, it's still the same distance, right? So we could draw the H out here, draw the H out here, okay? So to specifically define these, now that I've shown you in the pictures, height we'll call H, and it is the perpendicular distance from the base of the pyramid or cone to the vertex. Okay, where's the vertex? Right here. Vertex of a cone, vertex of a pyramid. Okay? Now, we also sometimes call this height the altitude. Okay, so this height can also be called the altitude as well. Okay. The slant height, which we say is called lowercase l, we'll look at separately. We'll look at for a pyramid, and then we'll look at for a cone, okay, to kind of help describe it most specifically, okay? So for a pyramid, here's the slant height, okay? It's the distance from the vertex to the base along a lateral face, okay? So you notice a pyramid, because, a pyramid is formed by polygons. Each of those polygons is a face, right? So on a cone, we have the outer edge of the cone that we can touch, right? That's a lateral area, but I'm not going to call it a face. Okay, so on a cone, we can say the slant height is the distance from the vertex to the base along the outside of the cone. Okay. Now, to kind of help you understand where we're going to go with this when we do some calculations, I want to just help you see, for example, let's say we were given whether we're dealing with a pyramid or a cone, the principle is going to be the same. If we're given the height on the outside, that's going to translate to knowing what the height is on the inside. So I could sketch that in here, and of course I would have a right angle here, okay, because these are right cones and right pyramids, We could also have oblique like we had with prisms, where we would not be at a right angle, we would be at some other angle, and the vertex would not be centered directly above the base, okay? But in this case, these are right. So this height is the same as this height, okay? And of course, this distance right here is the radius of the circle. So one thing we could do, let's pretend we were given the height and we were given the radius. If I wanted to know the slant height, you recognize what I've got here is a right triangle. And so we'd have a situation, for example, where you could say h squared plus r squared equals l squared. And you could use the Pythagorean theorem to help you find a missing part. So like, for example, if you were given the lateral distance, for example, the slant height, if you were given the slant height and maybe you were given the height, but you didn't know the radius, you could still use the Pythagorean theorem to find that missing information. And again, this works for both cones and pyramids, okay? All right, so to just kind of define a pyramid, define a cone, and then we'll do some calculations, okay? First of all, a pyramid has one base, okay? That's a polygon. So we can say it has one polygon base and lateral faces that meet at a common vertex. Okay, and if we want to calculate the surface area of that pyramid, we can take the area of the base plus the area of the lateral surfaces. Now you'll notice that the lateral surfaces are always going to be triangles. So we're going to say the area of the triangular lateral surfaces, okay? With a cone, we have one circular base joined to a vertex by a curved side. Okay, and so the surface area is going to be the area of the base plus the area of the curved surface, which is the lateral area. Okay, and so for a formula here, this you're going to need a formula for sure. So that's going to be the area of the base, which is a circle, so that's pi r squared, plus the area of the curved surface here is going to be pi r l. Now, you might wonder, where did I get pi times r times l? And that is beyond the scope of this course. However, if you're interested, you can either look up on Google, you can Google derive lateral area of cone, or if you're interested and you can message me and I'll give you a link where you can look that up as well, okay? But for right now, we're just going to accept that, okay? So I'll highlight that so we make sure we know what goes with what. So the area of the curved surface, the lateral area, is this portion, and the area of the base is this portion. Okay, so you don't want to confuse that with the area of a cone. So let's just kind of go back for a moment here. When we were looking at the surface area of a cone, okay, that was back here on the first page of this note guide. Here was the formula for, actually I've got it even, let's see, right up here, okay? So we have the surface area of a cone right here, which again, I showed you in two different ways, depending on whether you want to use the radius or the diameter, depending on what you're given, okay? So here's the surface area of a cylinder, okay? And you don't want to confuse that with the surface area of a cone, okay? So make sure you distinguish between those. because those are really, as far as formulas go, when you're dealing with surface area, those are your only specific formulas for surface area. The others, like for a rectangular prism where you're just adding up the areas of rectangles, or a triangular prism, you're adding up the areas of rectangles and triangles. Here you have more specific formulas, okay? All right, so let's do some calculations to calculate the surface areas of a cone, a square pyramid, and a regular octagonal pyramid. Okay, and I'm not going to pause here, but you might want to pause just to review your notes before you continue. Okay, so copy down your formula for the surface area of a cone. You've got the area of the circle, pi r squared, plus you have the lateral area, the side of the cone, which is pi rl. Okay. Here's the radius. The radius is 5 centimeters. So we're going to say pi times 5 squared. Okay. Here we've got pi times 5 times, now the lateral edge here, or in other words, the slant height, is 10 centimeters. So I'll just fill in that 10. Okay. So I'll get 25 pi plus 50 pi is going to equal 75 pi centimeters squared. And I'll leave that exact. I might as well. There's no indication I have to round here. Okay. All right, we'll look at a square pyramid here. Okay, this would also be considered regular, of course, because a square is a regular quadrilateral. So if I want to figure out the surface area of this square pyramid, I need to take the area of the base, which is the square, and I need to add in the area of the 4 triangles. Okay, when I say the 4 triangles, I mean the 4 lateral sides. Okay, so the 4 triangles, the lateral faces. Now understand this particular side right here, this triangle right here is, this one here is broken up into 2 triangles because this line right here represents the slant height. Okay? So this edge right here, this particular line right here, is the slant height. L. And we don't know what that is yet. Okay? But we do know what this height is. Now the thing is, this slant height is also the height of this triangle. And in order to find the area of these triangles, I need to know what this slant height is because it's also the height of the triangle. Okay? Right here, 10 is the base of one of the triangles, right? This length is not just the side of the square, it's the side of the square, and it's also a base of one of these triangles, okay? So I'm going to shade in 2 things here. I've got the yellow square is my base. So I'll highlight that here. And then I've got 4 triangles here. So I'll put that in green. So I've got kind of like overlapping that yellow base here. Okay, so that's a triangle there. Okay, so I have 4 of those and they're congruent to each other. Okay, so I can easily get the area of the square, right? 10 times 10. To get the area of the triangles, I'm going to have to do a little bit of work here. Okay, I've got 4 of them, so I know I'm going to multiply by 4, right? But I have to do 4 times 1/2 of the base times the height. Okay, well, this 10 here is a base of the triangle, right? The L is not just the slant height, it's also the height of the triangle. So I have to think about how can I get that height? Well, go back to what we were just looking at. Remember I said that sometimes in order to be able to find that slant height, you might have to do the Pythagorean theorem. If you know what the height is of a cone or of a pyramid, it doesn't matter. This applies to both because I can have, you know, basically this isn't a radius here. It's half of the side of the square. So if this side is S, this side is S over 2, right? But I can still do the same principle. H squared plus this length squared equals L squared, right? And so that's what I'm going to do here. Have to do a little sketching, okay? So what I'm going to do is I'll draw in the height. Remember I said sometimes you have to copy that height in? So that height is 12. And then I'm going to draw in the distance that represents half of, and there's a right angle here, half of the length of the side. So this is going to be 5 centimeters. So I have 12 centimeters, 5 centimeters, and then I need to figure out what this side is of the right triangle, okay? Now, some of you might recognize the Pythagorean triple, I hope, right? 12, 5, you might wonder what this is. So you can use a Pythagorean triple. Hopefully you might remember 5, 12, 13 is a Pythagorean triple that we can remember, okay? But you can use the Pythagorean theorem, okay? And I'm not going to write that out here because I know you can all do it. When you use the Pythagorean theorem, you'll get 13, okay? So we know that L is going to be 13 centimeters. And so now I can fill in what I need in my formula here, right? So remember the L is the same as the height of the triangle. That would be the H, okay? Here's the base of the triangle, which is B. So I have 4 times 4 of those triangles, 1/2 of the base, which is 10, times the height, which is 13. And now I can figure out my surface area. So I have 100 plus, when I multiply this out, half of 4 is 2, times 10 is 20, times 13 is 260, okay? And so my surface area that I'm going to get is going to be 360 square centimeters. Okay, so here was an example of where you had to do an extra step here to be able to figure out that slant height by using the Pythagorean theorem. Okay, so it's very important. I didn't show you the Pythagorean theorem because you know how to do that. You've done it hundreds of times, okay? Also, hopefully you might remember that Pythagorean triple 5, 12, 13. Okay, last example here we're going to look at is a regular octagonal pyramid. Okay, so in other words, the base is an octagon. Okay, now what I'm going to do is I'm just going to finish this off because it did get cut off on when I printed this for whatever reason. But I'll just finish it off and you guys can just do the same. I'm just going to kind of copy what's on the left side here on the right. Okay, and this will just continue down here, just copying top to bottom. Okay, it doesn't have to be perfect in general. This is what it's going to look like, right? And I'll just continue here. So you've got here and here, okay, and we're going to continue this. Here's the side that, or I should say the, this is 6 centimeters here. It's the distance from the center of the octagon to the side of the octagon, okay? So you can see that the height of this pyramid is the same as the distance from the center of the octagon to the side of the octagon. The exact same distance there. So what's interesting with that is that, you know, remember, as far as trying to figure out what the surface area is of this octagon, just like we needed, or the surface area of this octagonal pyramid, just like up here, we need that slant height. I can easily get that slant height here. I'm going to need that slant height because otherwise I'm not going to be able to get what the height is of each of these triangles around the lateral area. And I can easily get that slant height by just completing this triangle here. So I've got this triangle here, here, and if I just complete it to here, and I can also dash it in for you. If we complete that triangle, this distance right here, which is going to be at actually a right angle here, is actually the slant height. Okay, so if I break that out for you, basically what we're talking about is this. I took this triangle, 6 centimeters here, 6 centimeters here, and I can easily figure out what the slant height is. Think about that. If you have an isosceles right triangle, think for a moment before I tell you what's the measure of each of these angles. You should have immediately said 45 degrees. So if each of these lengths is 6, this is 6 times the square root of 2 centimeters. Okay? Now we're going to be getting decimal values in other parts of this octagon, but for right now I can leave that as a radical. Okay? So I know what the slant height is. The slant height is 6 radical 2. Okay, and again, you know, basically it's harder to see it on this octagon, but what you're looking at with this slant height is basically the same as on this square pyramid. It's this distance right here in pink. Okay, so I can use that same, I'll use pink again just to kind of highlight it. So it's that same distance there, it's just that triangle is smaller on the side. Okay, so to figure out what the surface area is altogether of this octagonal pyramid, we are going to do the same sort of thing as we did up here with the square pyramid. I want the area of the base. Okay, so I'm going to take the surface area is going to equal the area of the base, which is in this case an octagon, plus the 8 triangular lateral faces. So I have 8 triangles here, right? Remember up here it was 4 triangles. This time it's 8 triangles on the lateral faces. Okay, so basically if we want to consider, basically what you've got is, again, I can kind of yellow in the, it's already part of it's gray, but here's the base in yellow. Okay, and then the lateral faces are these triangles that you see around the side. And the specific one that we're looking at right here, because that's the one that has that hypotenuse of the triangle that I needed to find, right? That was that pink lateral or slant height right there. Okay, so we'll find the surface area by calculating the area of the octagon first. Okay, so we have to use what we learned in the last section, in section 11.3, about how to calculate the area of an octagon. And we have to remember, to calculate the area of an octagon, we need to know 1/2 the apothem times the perimeter. Now I can tell you something else that was caught off here is the length of each side of the octagon. The length of each side is 5 centimeters. So the perimeter is easy to get, right? The perimeter is equal to 5, there are 8 sides, 5 times 8, 40 centimeters. Okay, so that part's easy. Okay, as far as the apothem we will need to calculate, okay? So I want you to think about how to calculate the area of the octagon. I need to take a break just for a moment. So I'm going to just pause just for a moment and then we'll continue. Okay, so hopefully you took a moment to think about how you could calculate the area of the base, which is the octagon, with what information we had. Okay, so we had said the area of the base was 1/2 of the apothem times the perimeter, plus we have the area of the 8 triangles, the lateral faces. So we have 8 of those, and we're going to use the formula 1/2 of base times the height, and they're all the same area. Okay, so let's look at the 1/2 of the apothem times the perimeter. We already calculated the perimeter, which is 40 centimeters. Now, when we were working with this in section 11.3, we know we had to oftentimes consider that we have 360 degrees going around, and that we have, we can break this octagon up into 8 triangles, and 360 divided by 8 is 45, and then we had to divide that up and get 22.5 and so on, and we might have had to use trig in order to find the length of the apothem. Remember, however, that the apothem is the distance from the center to a side of the octagon, to the middle of the side of the octagon. And we already have that, okay? So it's hard to tell here, but this diagonal, this lateral distance right here is meeting this side exactly, okay? So this distance, 6 centimeters right here, is actually the apothem. Now, sometimes we draw it in this direction, right? If I drew it over here, that's still A is equal to 6 centimeters, okay? And that's where, you know, we'd break this up into triangles and so forth, right? We could break this up into 8 triangles going around, okay? But in this particular situation, I don't need to do that because I already know what the apothem is. So I know the apothem is 6 centimeters, the perimeter is 40. Now, as far as the base of each triangle, hopefully you can see here, if you look carefully, the base of the triangle is the same as the length of a side, right? So it's the side, but it's also B equals the base of the triangle, okay? So that is 5 centimeters. The height is the same as the slant height of the pyramid. So this is also going to be the height of the triangle. So that's going to be 6 square root of 2 centimeters. So I'm just going to need to do this calculation and I'll be done and I'll have the surface area. Okay, so basically 6 times 40 is 240, half of that is 120. If I multiply this out, 4 times 5 is 20 times 6 is 120 square root of 2. Okay, so you want to make sure order of operations wise you multiply here first. Now when I multiply that in my calculator, remember how you're going to multiply that. You're just going to say 120 times 2 square root equals, and you'll get about 169. We'll go out like 3 decimal places for now, 169.706. Okay, and if I add that together, to get the surface area, the final answer is going to be 289, and I'll just round to the nearest tenth, 0.7 centimeters squared. Okay, now something to keep in mind that I want to mention, and I'm just going to grab it here for you to give you just a bit of a hint. Okay, this is your 11.4 practice assignment. And one of the things you want to notice is where you're looking for the surface area of the pyramid here, you want to notice that in this particular case, this happens to be a hexagonal pyramid because the base is a hexagon. Unlike in this situation here, where we're actually given that apothem, so we don't have to calculate it, here you don't have the apothem. Okay, in other words, the apothem is going to be this distance right here. That's the apothem. Okay, and so you're going to need to calculate what that apothem is in order to be able to figure out what the area is of the octagon on the base. I mean, I could also draw that right here. Here, this side is 8. This is the apothem right here as well. Okay. So you want to keep that in mind. You're actually going to have to calculate the apothem. Probably what you'll want to do is to redraw the hexagon over here and work on it possibly labeling a side 8 inches, breaking it up into triangles. And then focusing on this triangle here and noticing that you have to calculate the length of the apothem here. Okay, you won't, in order to get the surface area, you need to know what that apothem is. Okay, also you notice here, and I think it might be true on the first page too, they tell you to find the lateral area and surface area of each prism and then round your answer to the nearest tenth. They're basically just giving it to you in parts. So if you find the lateral area and then you add in the area of the bases, you'll get the surface area. So if you find the lateral area first and then just add that into the surface area. What I'm most concerned about is you get that final surface area correctly. Okay. All right, so that'll do us for section 11.4. Thank you and have a good day.